As Igor mentioned in the email he sent out this morning, as host, you have a mean field approximation to Igor, which is me, Mark Alford, from Washington University in St. Louis. Our beloved host is on a plane to go and give a real, actual in-person talk that he gets to do. So I'm stepping in to host the meeting. And it's a great pleasure and an honor to do it. And it's a particular pleasure to welcome today's speaker. Today's speaker is Filomena Nunes, who is currently at Michigan State University. So she started in getting her PhD in nuclear physics at the University of Surrey, Guildford, UK, my hometown, where I am from, where I grew up. So I'm very proud of you, Filomena, as a product of my very own suburban environment. She went on to have a research position in Portugal and then became a professor at Universidade Fernando Pessoa in Portugal. Then in 2003, she came to Michigan State, to the United States, in the National Superconducting Cyclotron Lab, the NSCL, and moved up through the ranks there, became associate professor, full professor, head of the Department of Theoretical Nuclear Science, and then managing director of the FRIB Theory Alliance, which is what she still is now, which has been remarkably successful and has helped us recruit nuclear theory faculty here at Washington University, St. Louis. Along the way, she has accumulated honors. She's a fellow of the American Physical Society, a fellow of the American Association for the Advancement of Science. She's won awards at MSU, such as Inspirational Woman of the Year and William Beale Outstanding Faculty Award. And she's also received a service award from the Division of Nuclear Physics because of her service to APS. So it's a great pleasure to welcome Filomena to tell us why theorists are excited about exotic nuclei. So go ahead and share your screen. And during the talk, it's okay to ask short questions, but try to keep long ones till the end.
Hi, everyone. I want to first start out by checking the sound. Can people hear me okay? Sound is good? Screen? The screen is showing the whole thing?
Yeah, I can see it.
Okay, so thank you so much. I appreciate this opportunity to talk to a group of people I don't usually get a chance to talk to. And when I was asked to give this colloquium, I thought, well, I'm going to keep it basic and I'm going to try and transmit some of the excitement that is going on in the theoretical community, along with the start of operations of the facility for Rare Isotope Beams. So perhaps for this group, this is not so exciting, but I usually have questions in my colloquia so that people don't fall asleep. And this is one of the questions I had here. I wanted people to think about what was common here and get people focusing on the fact that all matter, the whole diversity of matter involves nuclear physics. And so what we're trying to do here is be able to describe the properties of matter and understand where all matter came from. And so those are sort of the underlying big questions that the field is trying to get at. And it all starts kind of hard because if you think of a neutron, the neutron decays, so that's not stable. You try to stick neutrons together, you can't stick them together. If you think of a proton, well, the proton is stable, but again, you can't stick many protons together. And so the key element really is this extra attraction that you get between the neutron and proton. And so this is a very naive picture. Some of you that actually develop nuclear models will laugh at this, but the whole idea is that it's this asymmetry in the nuclear force that allows you to then build up the ladder. Now, for us, all these are like building blocks, because what we're interested in is the whole landscape. And we represent the landscape always in terms of number of neutrons and number of protons. And the stable nuclei represented here in black are just a small fraction of all the matter that actually exists. We know a part of this, but there's a big part of it that we don't know. And so the facilities like the facility for isotope beams, what they try to do, they're like factories of isotopes where they try to get at these very exotic regions. And of course, ultimately, we can't produce this in a laboratory, but ultimately the most exotic of all exotics is the neutron stars. We know they exist and they have a massive amount of neutrons compared to the number of protons in their core, and they have an incredible density. So all this is within the purview of what we're trying to do when I talk about describing matter and where it came from. So we know what was produced in the Big Bang. We also have a good idea of what elements were produced in the oldest stars. And of course, we've got a very good idea of what we have here in our solar system. The question is, how did we get from the Big Bang all the way to the solar system? And that story is ongoing. That story is not resolved. We understand that there has to be, in order to get to the heaviest elements, there has to be explosive environments that are neutron rich that allow you to produce these heavy elements. Might be neutron star mergers, might be supernovae. We've got pretty good clues that both these sites do produce systems that are heavier than 100 mass, but how much and which is still an ongoing debate. And I show this picture that I particularly like that astrophysicists produced. In this picture, it's basically, as you recognize, it's the periodic table, but it's the periodic table. It's a very interesting periodic table where there is a time graphic of how much of this element came from different astrophysical sites. And so, of course, the lightest ones we know came from the Big Bang. And the heavier you get, the more you might get into these explosive scenarios. And it's really interesting to think of elements in this way, trying to understand where they came from. The problem is there's a large uncertainty with these models, and a good fraction of that uncertainty comes from nuclear theory. So nuclear theory is providing input to all these astrophysical simulations. And there's a lot of information in this slide, but let us, for example, focus only on abundances and the variance of abundances. What is shown here is for a neutron star merger. So these are models for the R process in a neutron star merger. And there are many different models that one can choose from that are available. They are density functional models, so bulk properties are encoded in this density functional. And what you see is that there's a huge disparity between the various models. So what the picture that I just showed you before is sort of an optimistic picture, in that there's really large uncertainty bands that come from the fact that the nuclear theory that goes into that is not fully pinned down. And so that's one part of the work that we've been doing. Another aspect is actually trying to understand the properties of these systems and how nuclei are organized internally. So in this plot, what is represented is the lifetime of the various isotopes, and you see that it falls down quite rapidly. And what eventually we would like is to be able to predict this from first principles, right? So you know, the theorist's dream is like, you give me QCD, and then I'll produce this landscape for you, right? That would be the dream. What ends up happening is you can't use QCD for this, but what ends up happening is we collect these stamps. Each isotope is like a stamp. There are measurements associated with these stamps, and we put them together and literally work in this puzzle within a theoretical framework, confronting it with all the stamp collection, trying to identify patterns that then can go back and inform the connection to the underlying fundamental theory. I want to point out that we don't know the limits of stability beyond charge 9. It's really not, you know, we know the limits down here, but we have no idea where the limits are up here. And I think sometimes people don't appreciate this. There's a lot that is unknown, and that's why we need isotope factories that can produce elements that are very far from stability. So this connection to QCD is really the thing we're aiming for. And of course, some very brave people are doing lattice QCD calculations and trying to get at nuclei with lattice QCD calculations. Here is a not so recent result on the magnetic moments for deuterons that I found very impressive. But you know, there is certainly effort going on trying to get at the light elements from QCD directly through lattice techniques. However, you know, obviously I'm interested in lead isotopes and bismuth isotopes and uranium isotopes, and this is not the right technique. So the really paradigm shift, I would call it a paradigm shift, that happened in our field, in part due to Vera that has joined here, is this understanding that we can use effective field theories. And so there are the energy scale at which, you know, quark degrees of freedom play a role, have nothing to do with the energy scales in which we worried about for uranium excitations, for example. And so the fact that we've got multiple energy scales here allows us to build theories that dial the resolution that we need in our theories. And so you can still build on QCD, connect to QCD using effective field theories to get at nuclear forces that have the underlying symmetries, but only include the degrees of freedom that are relevant for the problem. So with that in mind, then we can build a nuclei with this tree. So the picture of the tree is QCD is our root, the trunk is the effective field theory, and then we get the fruits. And the fruits are all the isotopes. And with this thing in mind, I have a couple of examples of how the field has been able to produce results that are very impressive. On one side, I'm showing many body calculations for a bunch of different isotopes going from the alpha particle to calcium-40. And what is shown is the binding energy and the RMS radius of the charge radius of the system. And you see that for a particular effective field theory interaction, you get a pretty good description of the data. You get really, so that this means no knobs. You have no knobs to play with. You're just doing a many-body calculation for the nucleus based on the effective field theory that obviously with some truncation level, but the effective field theory that satisfies the right symmetries of the problem. You can also do scattering. So this is the no-core shell model version of the many-body calculation, but where you're actually doing a scattering calculation, which is obviously more challenging than doing the bound state calculation. So the field is really shifted from using what people used to call phenomenological forces to forces that are based on QCD with effective field theory. The other thing that the field has been having a lot of fun with is what happens in these extreme cases of weakly bound and, what we call the drip lines, the limits of stability, when you add so many neutrons that you're out there hardly connected to the central core. And so, it's very easy to understand for us that know quantum mechanics, that once your binding energy becomes very close to zero, you actually get this very extended wave function. And that means that your system is spending most of its time in classically forbidden regions. The sorts of models that we used to have previously of the nucleus is completely inconsistent with this. And so the methods, for example, that expand on harmonic oscillators need to completely be revised to include continuum effects in these long tails. And so we've seen a lot of that. And to me, the most exciting manifestation of this are the halo systems. So here is an example of a halo, lithium-11. If you actually try to build, on the lithium chain, just add neutrons to the stable lithium isotopes, you actually don't change the size of the system. The system is pretty much constant in size as you add those neutrons. But suddenly there's a huge jump, and that huge jump really means that the additional neutrons, those valence neutrons, are now hanging out in some halo around a core. And so this picture is not a unique picture for lithium-11. It is actually a picture that we see all across the drip line that has been studied so far. You see here coded in pink all the halos that you get on the neutron drip line, and in blue the halos that have been identified in the proton drip line. So this is very interesting phenomenon that has appeared as a consequence of this extreme of weakly bound systems. And then, of course, I could also talk about the unitarity limit and FMOF states, but there's a limit to what I can discuss in 1 hour. So the limits of stability have really posed a particular challenge for these many-body methods that were really designed for compact model of the nucleus. And I'm showing you a recent review, some results that were presented in a recent review, where different many-body methods, and actually not just many-body method, different ab-initio methods and phenomenological many-body methods were confronted with data. And so what's presented here are the calcium isotopes, and it's the 2 neutron separation energy for a bunch of calcium isotopes up to a point where there was data. And all these methods were compared to each other. And I'd like to highlight what was the best of the set was the in medium SRG that had the most advanced effective field theory and then chiral force. And that, as you see, had an incredible, fantastic performance for all these isotopes. And so the question is always what happens when you go into regions where experiment has not managed to go. And so that this method in particular, of course, they could calculate beyond, and they did calculate beyond, and later the experimentalists went and measured it. And so it started to show the shortcomings of a force. And this is, if you're going to take home anything from this, it's the idea that when you go out very far from stability, the sensitivity to details of the nuclear force that you didn't look at before, they are unveiled. So the limits of stability really pose constraints in aspects of the force that may not play such an important role in the stability region. And so that's really where the field stands, is trying to come to terms with what are those aspects of the nuclear force that will need adjustment. And it's really a feedback loop between theory and experiment in this process. The energies, binding energies and separation energies are not the only observable. And in fact, they may not be the most sensitive observable. So here is a charge radius or the proton radius shown for we're just showing here in medium SRG results, but now for different chiral forces. And what you see is a strong sensitivity on the chiral force. So we have observables that just seem to immediately lift degeneracy between all these chiral forces and allow you to start looking more deeply as to what is it that you need to correct in your interaction, in the way you're building this interaction. So the ab-initio calculations of nuclei have really seen an incredible technological advance. In 2010, less than 20 years ago to 15 years ago even, only a few nuclei could be done ab initio. And over the last decade, this has just increased tremendously. Heiko just gave me the slide yesterday, and you can really see how it's accelerated in the last 4 or 5 years. And what might have gone unnoticed to this audience is that little dot there. I really want to highlight that little dot there, is that we've actually managed to calculate lead-208 ab initio. So that's like an incredible feat. So we're moving up this ladder with the technology as more and more smart people come on board and think of ways to beat the exponential factor that goes with increasing the number of neutrons and protons in the system. Okay, so then in addition to having this understanding of what goes on as you start to seep into the no man's land, what I call the no man's land out here. Actually, let me just stress this, because sometimes people don't quite appreciate it. We don't, ab initio calculations cannot go out here. There's no way. So we have density functional theories that can go out here and make predictions out here, and they're very uncertain. We don't really know where this is. What they do predict is that if you think of what we know as the continental stuff, and if you think of beyond stability out here as the sea, as the ocean, and this region here as the beach, you've got to go through as much beach as the whole United States to get to the shore. That's sort of the idea, is there is more out here than there is in here. And this is a long way. There is many neutrons that you have to add to the system. So this is hard. This is very hard. It's hard from the theoretical standpoint. It's hard from the experimental standpoint. And so it's really, this is not the case down here, right? So if you're talking about light systems, it's very different. It's closer. But if you're talking about heavy systems, getting to the drip line for heavy systems is really hard. And this is part of what we're trying to do with new facilities. But in addition to this, there's something else happening up here that is predicted by these density functional theories, and that is an island of stability of superheavy nuclei. This is fascinating, because if there truly is, if theory is right, and I'm a theorist, so obviously I'm biased, I think it is, if there is such a thing, once we produce these elements, we might be able to use them. We might actually be able to use them for something. And so a part of the community is actually trying to strive to get there. And there's been progress. So I'm just mentioning in this slide some of the things that have come to bear fruit. New elements have been confirmed and put in the periodic table. some elements have been discovered, and this is ongoing. You know, I just checked yesterday to see what was the latest, because I don't always read these papers, but it's an ongoing effort. A lot of the work is happening in Dubna, but there are also groups in the US that are working on these topics. I have to mention the benefit from society, because that's something that a fraction of our community is also worried about. And I always quote this report from NSAC on isotopes, because it is very extensive on the many ways in which nuclei can benefit society. And so if you're interested in this, I think this is a good document to go back to. So there's all this plethora of opportunity in theory. And so the question is, how are we going to measure this? Because, you know, theory, of course, is all very good, but ultimately we would want to confront with data and do the natural cycle of the scientific method between theory and experiment. And so here is a plot that's a little old. This used to be known isotopes and estimated possible given a given density functional theory. So exactly this light blue, exactly where it stands can change depending on the density functional theory. But the point being made here is that we only know a small fraction of these. Of course, the facility for isotope beams exists because we only know a small fraction and we want to know the whole thing. And so the idea is that FRIB will be able to produce a large fraction of this unknown region. And so the facility, for those of you that aren't familiar with the facility is sitting right behind me, behind my office. My office is somewhere here. The facility is down there, and it's a paperclip format of accelerator sections like these. We've got all these quadrupoles, and in a clip type of format, accelerating beams, and then smashing the beams on a very hot target, and creating all sorts of the fragments or the high isotopes that then get collimated to the experimental vaults. So the idea is that this facility will be able to produce about 80% of these unknown isotopes. And so the expectation is that with this facility coming online, there really should be a paradigm shift in how we understand matter, because we've never been into these unknown regions. The first experiment has run, and the facility has been running since June 2022. The first one was a measurement coming from fragments of calcium-48, and they were measuring the beta decay. So the fragments would be implanted on the detector, and then the very granular detector could measure, even with small counts, measure the lifetime of the system. My research is in reactions, and so I felt compelled to, at least towards the end of the colloquium, add a few words on reactions. We're talking about isotopes that are rare and unstable, and therefore most often what we can do with them are reactions. And so the way to learn about the properties of these systems is really to impinge them on a target and then see what comes out. And from the pattern, you know, from the results of the reaction, we obtain information of the properties of the original system. One of the things that we play with a lot is the energy. FRIB is able to produce beams with low energy all the way to high energy. And this is a great advantage because one can think of this energy as allowing for deeper penetration in the nucleus. And I talk about tomography of the nucleus in this way, because by doing reactions at different beam energies, we're actually getting information about different regions of the wave function. Part of the work that I do connects strongly with astrophysics, because many of the bits of information that are needed for those astrophysical models that I mentioned in the beginning rely on indirect methods that involve measuring a reaction with a rare isotope and then connecting it back to the astrophysical rate or to the astrophysical property of interest. And so for one thing that we need for astrophysics is the isospin and density dependence of nuclear matter. How can we get at this information? Well, one way to get at this information around the region where we can produce isotopes is by charge exchange. So by doing a reaction like PN, we can probe isospin dependence of the nuclear properties. And of course, if we're interested in something that has higher density, like the connection to a neutron star, then we might do heavy ion collisions of these exotic species. One of the most important inputs to neutron star mergers or supernovae are neutron capture rates. This is part of the network, the nucleosynthesis network that goes into these. Neutron capture rates on unstable nuclei are impossible to measure. The neutron, as I mentioned, decays, and the exotic thing that you're trying to measure this capture rate on also decays. So there's no way to make this work. So there are indirect methods to get at this information, and they involve reactions. So one indirect method is to measure the inverse process. And so if you're trying to get at the nucleus A, the N gamma on nucleus B, you can look at the reverse process in the photon field generated by a heavy target. Alternatively, you can measure the neutron transfer, and from neutron transfer infer the N gamma. And so these well, first of all, you've got to do this measurement, and then you've got to work with your reaction theorist to make sure that you understand how to translate that into the astrophysical quantity of interest. Same story goes for the proton drip line. So there are many P gamma rates that are important for novae that are very difficult to measure directly, because the reactions, as we all know, in the gamma window, in the relevant energy regime for these reactions, the reaction rates plummet down logarithmically. So it's really hard to measure these things directly. And so indirectly, you can do proton transfer reactions, and from that infer the P gamma rate. And so part of my work is developing the theory that goes together with this. And finally, electron capture rates are very important for supernovae, and we also have methods that involve reactions that can get at this information. So the important simplification that I need to talk about when I talk about reaction theories for heavy systems is what I'd like to discuss next. So as I pointed out in the beginning, there are ab-initio approaches to calculate reactions starting from, for example, chiral and N forces. However, these methods cannot be ported to heavy systems like uranium, like understanding a uranium interaction, or even a lighter system. So the question is, what do you do if you can't do the full ab initio? And so what typically we do is we put another level of effective field theory on top of our already effective theory, right? So it's another level of effectiveness where we freeze degrees of freedom that again are less relevant to describe the process of interest. And so we reduce the problem from a many-body problem to a few-body problem that then is tractable and can be solved for the scattering process of interest exactly. And so in doing that, what we are introducing is new effective interactions that now are between nucleons and nucleus. And these effective interactions carry with them uncertainties. So they call typically optical potentials in our field. And in the past, they were very much phenomenological. So based on large bodies of data that were fitted, and these interactions were extracted. And what we're seeing more and more now, there's really a movement of the ab-initio community to try and extract these optical potentials from many-body theory. These continue to be one of the main sources of uncertainty in our predictions in reaction theory. And so I've done quite a lot of work to try to quantify those uncertainties. And here is just one example of the work we did. We actually compared a Bayesian analysis of the optical potential with a frequentist approach and showed that the uncertainties that in the past people thought were small, relatively small, if you actually do a Bayesian analysis, you end up with much larger uncertainties, and that the Bayesian analysis is actually a more reliable quantification of the uncertainty than the frequentist. So I'll just walk you through to all the information that's in the slide, which is probably overwhelming, but there's 3 different reactions. They all elastic scattering, so very simple optical model kind of solvers. What is calculated is just a differential cross-section as a function of angle. And you see that there is data for this. The data is included in the likelihood, and we get distributions for the parameters, and from those we can extract 95% confidence intervals for the observables. And that's what's actually plotted in this on 95% confidence intervals given the data. And what you see is in orange the Bayesian approach, in dotted the frequentist approach, and what is shown here is just the width of this 95% confidence interval as a function of angle. And you see systematically the blue is below the orange, which tells you that the frequentist approach, which is basically the old way of doing uncertainty quantification, doesn't really give you the right uncertainty quantification. What is shown here is what is called the empirical coverage. It basically is if you're doing a 95% confidence interval, 95% of your data should be inside the interval. And so it's basically, this line is that perfect behavior. And what you see is that the frequentist is systematically well below that, and that the Bayesian, at least in the high confidence level, is very close to being correct. And so the message from this study actually was, we should really be doing Bayesian analysis on our reactions in order to get a true quantification of the uncertainties. And I just want to mention the Bayesian analysis of nuclear dynamics collaboration, that is a framework that has as a goal to develop the software that will be more general than just nuclear reactions. It'll be able to do basically anything nuclear related. Once there is a model and some data, it will provide ways of doing the emulation of the problem and the calibration, and eventually provide sort of parameter distributions and a full understanding of the statistics around the particular problem at hand. So I just wanted to mention that in case you're interested in this sorts of stuff. The webpage is quite detailed. So I'm going to finish now and just say that it's, in my view, quite a perfect time to be in this field. Nuclear theory has really evolved from being a very descriptive theory to actually having the potential of being very predictive in regions where we can't go experimentally. We are achieving this because of the ability to root the theory in QCD, and also the shift to quantify uncertainties honestly. It's also exciting for the experimentalists, of course. There's a new facility, and this facility is going to get to all these unexplored regions. So the expectation is there'll be many surprises, and they'll come knock at our door when things don't look reasonable, and then we'll be scratching our heads for a while. And I think that's just the fun of it, really. So I'm happy about that. So I'll stop here. I thank you all for your attention, and I'm happy to answer any questions.
Okay, so thank you very much, Filomena, for that very nice overview. And if anybody has a question, please go ahead and hit the reaction button that raises your hand. I have a couple of questions actually that I can sort of start us off with. One is, so you talked about, so chiral effective theory is this tree trunk, right? So what are the limits of applicability for chiral effective theory? You mentioned it a couple of times, but you know, what makes some nuclei treatable that way and some not?
Yeah. So there are two aspects to this. The first one is whether you can actually solve the many-body problem, right? So the efforts have been progressing so fast in that respect, right? And this illustrates the effort is, you know, can you solve the many-body problem when you go from A equals 10 to A equals 40 to A equals 100 to A equals 200, right? That is one challenge. And I have to say that many of us wouldn't have predicted it would have moved so fast because of this exponential growth with the number of nucleons. So this is very, very difficult to handle, right? As you add, but the techniques that have been developed, the new techniques that have been developed now have a polynomial growth instead of exponential growth. It's much better. There's also a lot of smartness in the technology of all the anti-symmetrization aspects and so on. So my sense is this will be bridged. This will be bridged. Is like this eventually, all these smart people, they'll figure out how to do this. The harder problem is what happens to the interaction, right? So you can solve the many-body problem for 208 nucleons, right? For the lead, 208 nucleons, but you might have the wrong Hamiltonian. You might be solving the wrong problem. And so the question is, how do we pin down this force? A force that is rooted in QCD, can it really do the job for lead 208? And I think that's a much harder problem that the field is grappling with. And it's certainly already showing some of the pathologies that these forces, as we move up to heavier systems, are showing problems like saturation density, you know, saturation properties in nuclear matter are wrong, radii are wrong. And so there are things that we'll need to learn about how to construct this force while still, you know, while still being the tree trunk, while still having the tree trunk, having a tree trunk that can really go to all sorts of fruits and not just the light fruits.
Okay. Henry de Jong.
Hello. Thank you very much for a good talk. I have a couple of questions. Years ago, there was a talk at ASU on TZO's Thorne, I believe it's Thorne-Zitko objects, where essentially a neutron star is absorbed and gets drawn into a red giant. And that was supposedly able to, or theoretically able to produce certain elements that no other astrophysical process was able to produce until then. And then another question I have is, can you give some examples of some nuclei that have been found in astrophysical processes that were totally new or unexpected or are not able to produce or known on Earth at the time?
Okay, so on the first question, I don't know anything about it really. So I can't comment because I have not heard about this process that you just described. On the second, so it is hard to use astrophysical observations to isolate particular isotopes that are short-lived. What we do have are nucleosynthesis simulations. And so from the nucleosynthesis simulations that are consistent with the observations, So astronomical observations tend to already have things that are not nanoseconds lived, right? And so from the models that are consistent with those observations, then we can infer what are the rare isotopes that were in that path. And yes, we do that. And actually in some of my slides, if I can go back, let me just go back, because I think I have some slides where I show a line. I think this one is an example here. I didn't highlight that, but you see this line here that is represented is...
We're not seeing a slide.
Oh, I'm sorry. Thank you so much for telling me that I forgot to share. Okay, can you see it now?
Yes.
So this line here is what the models predict to be the R-process isotopes, the isotopes that are generated through the R-process in these neutron star mergers. And so we know from those models that all these things have to have existed in order for the heavy stuff to have been produced. So I don't know if this is the answer you were looking for, but this is how we are able to make that connection with rare isotopes.
Yeah, it's sort of an indirect way, but the reason I asked this is, again, the classic example I think of is the detection of helium in the solar spectra, unknown prior to that on Earth. So that's why I was just wondering. Okay, thank you very much. But you might want to look into TZOs.
Okay.
I believe one has been detected, supposedly. I'm not up to date on it, in one of the Magellanic Clouds. So, and I believe the observatory in Arizona up there was one of the places. And I believe the astronomer's name is Massey, M-A-S-S-E-Y. But
Okay.
this was like probably 5 or 6 years ago. But that was a fascinating process.
Thanks.
Thank you.
Okay, any other questions anyone would like to ask at this point? Actually, can I sort of follow up on something that came up in your answer there? So you mentioned halo nuclei as being good probes for theorists, but I was just wondering, do they play any role in like astrophysical phenomena, nucleosynthesis? Do we need to know how they behave for some reason like that?
Yeah, so if we think of abundances, if we think about solar abundances, for example, for the light systems. So first of all, let me just preface by saying we know nothing about halos for heavy systems or intermediate mass systems, right? Because we've never gotten that far. We've never walked the beach all the way to the shore. But for the light systems, we know quite a few. And are these relevant for the production of the light elements? And the answer is no. To a large extent, no. Because for the light elements, we kind of know that this proceeds in the pp chain, and then and then the alpha capture, and you bridge. So we know how we make it all the way to carbon 12 and then to oxygen 16, and it's not exotic. That part is not exotic. So regardless of this, if you're interested in other things and not just abundances, then there are ways in which these nuclei might have a role in producing seeds for the heavier systems. And so there's some work that has actually tried to develop. So I've done some work myself, but other groups have also done some work in upgrading, let's say, our understanding of captures on such exotic systems, where you can't really think of it naively as being one core, because these halos have these strange halos. So yes, so there's some work in that direction, but it's not so much for the abundances of the light elements.
Okay. Any other questions? Mileto.
Okay, thank you for your nice talk. And I have two questions. It is possible to have anti-nuclei. Is there experimental evidence on their stability? This is the first question. Second question, when two nuclei collide, the oscillations result with frequencies on the order of zeptoseconds. What role does a giant dipole or quadrupole resonance play in the nuclear transitions?
Okay, so for the first question, we certainly have no way of producing these anti-neutrons in the facility for isotope beams. This is not why it was built. Could we do it? I don't know. Would it be interesting? Yes, but because I'm just curious. But I don't know. Now, of course, a facility like JLab is interested in.
It's possible to have a anti-galaxy, I think. It's impossible.
Well, it's possible, although never observed, right? So this is it fits in the theory where I'm not sure we want to spend a lifetime investing in if there's going to be no observations. What if, so the sort of physics that I'm involved is low energy scale nuclear physics, but facilities like JLab, they're interested in producing hadrons that are exotic in multiple ways. And so they're even if they're not antiparticles, they might have some strangeness or some other aspect that is a different sort of exotic, right? So when I talk about exotic nuclei, I'm talking about larger symmetries between the number of neutrons and protons. Other people might think of antiparticles or strangeness or other things. So just want to make that clear. Your second question, sorry, I forgot. Oh, about the giant dipole and quadrupole. I now remember. The phenomena of
Yes.
giant excitations obviously is also present in these exotic systems, and it is being studied. I don't know that there's anything, more to say, but if you have halos that are sticking out of some core, obviously you've got a mode that is attached to halo degrees of freedom and core degrees of freedom, right? So you get phenomena that are different than the sorts of phenomena you could get for these stable systems. I don't know if that's what you're interested in, but.
But what is the limit of energy that involve giant dipole?
Oh, the
Energy for
the sorts of energies of these giant dipole things is of the order of tens of MeV, and typically for these very exotic systems, they tend to shift to lower energy. So they're not very high energy. Like, depending on your scale, they certainly not GeVs. They tens of MeVs.
Okay. Thank you very much.
Okay. Any more questions for Filomena? If not, then we're just getting to the 1 hour point. So this is a good moment to say thank you, Filomena, for that wonderful talk. Thank you to the audience for coming.